So last time we talked about Gauss's law, and I'll remind you, Gauss's law is the electric flux through a closed surface is equal to the charge enclosed by that surface divided by that new constant epsilon naught. And really, these are vectors. So Gauss's law is always true. For any closed surface, the electric flux, this total thing, is equal to only the charge enclosed divided by epsilon naught. But we don't really care about electric flux most of the time. Most of the time we want to know about electric fields, which means we need to be able to actually perform this integral. So we are going to start with a hollow sphere. So this is a hollow sphere. And I want to find the electric field. Oh, I should write this. This is a hollow sphere of radius big R. I want to find the electric field right here. That's about half of the distance between the center and the outside, and I'm going to call this little r. So I want to find the electric field right here. To do that, applying Gauss's law, I need to draw a closed surface, so I need to draw another sphere that is at this distance from the center. So I'm going to draw another sphere. Now, here's what gets interesting. There's no charge in there. Remember, this is a hollow sphere, so all the charge on it is smeared out over the outer surface. There's no charge inside because there's no material inside. There's no place for the charge to be. So Q enclosed equals 0. So this electric field must be 0 because there's no charge inside. If we go outside the solid hollow sphere, so I'm going to redraw it. So same big R, same Q. But now I'm going to go out to this location. So at this distance from the center. So now when I draw my sphere, my charge enclosed equals Q. So now I can actually perform this integral. Now, the thing to notice about this is my electric field points everywhere, assuming Q is positive, outward. And at every point that it crosses my blue Gaussian surface, it's called, it's headed directly outward. It's always perpendicular to, well, that one's not very good. It's always perpendicular to the surface that I drew. And I'm at the same distance. So the electric field is constant. So I can take this equation and pull the electric field outside. The reason that's powerful is because now we have the integral of a derivative. And so this is just the electric field times the total surface area of this sphere. And we've already said Q enclosed is just Q. So area of a sphere, is 4 pi r squared, and we have two r's in this problem. So I'm calculating the electric field at this location, so that's the sphere I'm referring to, the blue Gaussian surface. So this is 4 pi little r squared equals Q over epsilon naught. So if I rearrange, equals 1 over 4 pi epsilon naught times Q over little r squared. So what this says is, if you have a hollow sphere of charge, when you're inside the sphere, because there's no charge enclosed, there's no electric field. When you're outside the sphere, you do enclose charge, but you enclose all of it. And let's explain why we measure to the center. The size of this Gaussian surface, we measure from the center because that's just convenient. We usually measure the total size. But more importantly, when we calculate the surface area here of this Gaussian surface, this is a sphere, and surface area of the sphere, the equation 4 pi r squared means r measured to the center of the sphere. So what we're really doing here is saying that if you're outside a sphere, it doesn't really matter how big the sphere is. Big R didn't show up in this equation. If we're outside the sphere, it's just like a point charge. And of course, you know a point charge is E is KQ over R squared. And you remember from the last one, K is 1 over 4 pi epsilon naught, so they're the same thing. So outside a sphere is just like outside a point charge. Inside a sphere, a hollow sphere, there's no charge inside, so the electric field is 0. And notice the way I drew the electric field. It starts on all these point charges. But there's nothing inside because, like, say there is one, but like from this positive charge would be to the right, from this positive charge would be to the left. They cancel out. So yeah, I could draw all those electric fields pointing inward, but they all cancel each other out at every point, so there's no point of drawing them and then erasing them. So now we're going to go to a different situation. We are going to do a solid sphere. So I'm going to make it the same size, same big R radius, same even amount of charge. I'm going to really, really lightly. It's everywhere in there. So there is an electric field pointing outward from everywhere, including from the center, because there's charge here, there's charge here, there's charge here, there's charge here. So there's charge going everywhere. So I want to know if I'm only this far from the center, distance little r, what's the electric field there? So I draw my 3D surface, and then I write down Gauss's law. EdA equals Q enclosed divided by epsilon naught. Now, because we've drawn it at the same distance, we know the electric field's the same strength because of symmetry. There's no difference in this side and this side. Okay, pretend there's no difference in this side, that side. Make sure they're perfect spheres. So we already know how to handle the left side of this equation. But the right side, Q enclosed. Q is the total charge that is distributed throughout this sphere. So I only want the charge inside the blue dotted line. So to get that, I'm going to do a ratio. The charge enclosed divided by the total charge. Let me actually even write total there. So this changes, the difference between this and the whole thing is a difference in volume. So we're going to do the volume enclosed over the total volume. Because if there's charge everywhere, it's not just like along a line where you'd say the radius, and it's not a circle. Remember, these are not circles, these are spheres. So the volume enclosed by that charge is proportional to the charge enclosed. So Q enclosed over total charge we've said is just Q. Well, the volume of a sphere is 4/3 pi r cubed. So the volume enclosed is 4/3 pi little r cubed. The total volume of the sphere is 4/3 pi big R cubed. So the constants cancel, and we can rearrange and write Q enclosed equals Q times little r cubed over big R cubed. And then we apply Gauss's law. We can take the electric field out because of symmetry. It's the same strength everywhere and the same always normal to the surface. It's always crossing in the same direction as the normal or perpendicular to the surface itself. So we need to do times the surface area equals Q enclosed over epsilon naught. So now the surface area. We are talking about finding the electric field on this blue surface. So we need the surface area of little r sphere. And surface area is 4 pi r squared. So this is 4 pi little r squared. Equals Q enclosed is this equation, QR cubed over big R cubed, and then we also need to divide by epsilon naught. So we usually rewrite this, pulling the 1 over 4 pi epsilon naught to the front, and then we have a Q, and then notice the R's. This is an R squared, this is an R cubed. So this goes away, and this is just R to the first power. But we do keep big R cubed on the bottom. So what this equation says is if you're inside a solid sphere of uniformly distributed charge, the farther you go from the center, the bigger the electric field. Now, right when you get to the surface, things are a little different. So when we go to the outside, So we redraw the sphere again, and we fill it in. Oh, I did that a little darker than I meant to. But we know the electric field points everywhere outward. And now I want to do a point way out here. So when I draw my sphere, this is little r. And of course the sphere itself is big R and Q. Well, now when I apply Gauss's law, E dot dA equals Q enclosed over epsilon naught. So I'm going to skip ahead. E times the area of the sphere of interest, the blue sphere, so 4 pi little r squared, equals, well, the charge enclosed is big Q over epsilon naught. So we get 1 over 4 pi epsilon naught Q over r squared, which is exactly the same thing as we got for a hollow sphere, which is exactly the same thing we got from a point charge. So if you have a charge, you know it's located there, size, but if you're outside of it, you don't know from measuring the electric field whether it's a hollow or solid sphere. It acts as if all of the charge was concentrated at a point at the center, because this is the exact same equation as the electric field of a point charge. Inside, things are different, but outside, you can't tell. And this is leading us into some things with conductors that we're going to do next class period. So, turn the page. So we started this class with points, and so we just went to spheres. And then we also talked about lines of charge. So if I draw a line of charge, and remember for a line of charge, we talk about the charge per unit length of charge divided by length. So you know from this line, assuming this is a positive charge, that the electric field points outward everywhere. And please remember this is three-dimensional. This is not a line with things next to it. Well, it is a line, but they don't only point left and right. They also point at every other angle, making a complete cylinder, like that model I drew. So I want to find the electric field around this. So to do so, if I want to find it here, well, now I need to draw my Gaussian shape. But in order to apply Gauss's law, I need to be able to pull the electric field out. So I need the electric field to be constant. So my shape needs to be at the same distance from the line. And then it's got to be 3D, so it's got to be the same distance on the other side. This is not a rectangle. Remember, this is a 3D surface. This is a cylinder. Because the cylinder, every point on the curved surface has the exact same electric field strength. So applying E dot dA equals Q enclosed over epsilon naught. On this side, my surface area equation ends up being this curved surface of the cylinder. We don't have to worry about the end caps because there's no electric flux for the end caps. There's no electric field pointing to the left or right. So we just need the curved surface. So the area of this curved surface is the circumference of the bottom times the length. So I didn't put length on here. So let's define L. So this is 2 pi r, circumference, times the length. Well, then the charge enclosed. Well, usually, again, with these, we do lambda, which is charge per unit length. So the charge enclosed is equal to this L, the specific L, this is a general one, this L times lambda. So L lambda, and then I divide by epsilon naught. So we get 1 over 2 pi epsilon naught, lambda over r. Notice the L canceled out. And that's good because if I'm looking for the electric field here, as long as I'm looking at it fairly close to a really, really long line, it shouldn't matter how long this section is that I did. Now, we already did the electric field for a long straight line, and we got 2k lambda over r. So we get 2k because this is 1 over 2 pi epsilon naught, not 1 over 4 pi epsilon naught. So that's where the extra 2 comes in. You have to multiply this by 2 to get k. But now, what if we have a cylinder of charge? fill it in really lightly. So a cylinder of charge. If you're outside the cylinder, it's exactly like this. We don't need to redo that. But if we're inside the cylinder, so this cylinder has a total radius of big R, and I want to find the electric field here, which is at a radius from the center of little r. Well, I draw the same idea of a cylinder to be symmetric around the center, because then my electric field is the same strength everywhere. So what gets tricky here is figuring out charge enclosed. So, sorry, just want to make sure. We do the same volume distribution. So Q enclosed over Q equals V enclosed over B total, Q total. So Q enclosed over the total Q charge, whatever it is, for maybe this section, but just go with the total charge. If this is, again, L, now we need the volume of the cylinder. The volume of the cylinder is the area of one end times the length. So it's pi little r squared times L. And the volume of the whole thing for this length would be pi big R squared times L. And again, L cancels out, as is helpful that it does. Well, so does pi. So Q enclosed equals little r squared times Q over big R squared. So when we do E dot dA, make sure that's on the screen, we know this is E times the surface area of the curved surface of the Gaussian surface. So 2 pi r, little r, times L equals r squared Q over big R squared. Don't forget the epsilon naught. I forgot to write it over here. And so to finish this, E equals 1 over 2 pi epsilon naught. One of the r's cancels out, but we have Q over L, and I'm writing that way on purpose, times R over R squared. This is our lambda. Wanted to recover that. 1 over 2 pi epsilon naught lambda R over big R squared. So inside a cylinder, similar to inside a sphere. Last comment I'm going to make, because your class is actually about to walk right in. Gauss's law is always true. Unfortunately, it's only useful in these two situations, and you can also do it for a plane of charge and rederive that. I'm not going to do that today. You could look in your textbook or online if you really, really want to see it. So Gauss's law is always true, but I've actually shown you almost all the situations where it's useful to separately calculate the electric field. Other charge configurations, because you don't have a beautiful symmetry, if you can't pull the electric field out of the integral, you can't separate these. You can't actually apply it to find an actual field expression. But you'll be working on these. You're going to do an assignment on paper for this one. So see you next time.